Hey Stats fans, it's time for video number 37. It's just you and me today, so that's okay. We'll take care of business together. Mr. Lewis, off having fun someplace. All right, today we're going to talk about what does best mean. What I'm talking about is the line of best fit. Our goal is to draw a line through the data as close as possible, and we need to come up with an exact way of saying how good a line is. Okay, so like I just said, the goal of linear regression is to find a line that fits the data. And there are several names for this line. There we go. So the very first name of it is linear regression line. So this whole process is called regression, fitting a line or a curve to data. So the linear regression line is the line that of best fit. That's another name for it. And yet another name for it is the least squares regression line. There might even be more names for it. It's a topic, a very famous topic and a very famous procedure, so it's used in a lot of places. Today, we're going to learn what this least squares is referring to. Why is it called the least squares line? So by the end, hopefully you have a clear idea what we mean by the best line. Okay, now there are actually several different ways to determine how close a line comes to points. And we have to be clear about what kind of distances we're talking about in our graphs. The first way is to use vertical distances. So what we could do is talk about how close vertically the line comes to the data. Here we have 4 data points and a line drawn through them. We want to measure how good the line is. So we might talk about how far away the line is vertically from the points. The second graph is another illustration of that. See how the vertical distances are drawn in? So we could use that. The line that kind of has the smallest vertical errors, these are like errors, how much it missed the data by. The line that has the smallest errors might be considered the best. Here's another way. Actually in geometry, this kind of geometric way of determining a distance from a point to a line. To find the distance from a point to line, you got to find what's called the perpendicular distance. The distance in the perpendicular direction to the line. Like this figure over here kind of shows it, we can really see it. So you would draw line segments that make a right angle with the line and measure those segments. Now, there are a lot of ways to determine how close the line comes to the points. But we're going to use this first one. And this is the basis for what's called the method of least squares. Okay, so we're going to be talking about vertical distances. And vertical distance is the change in y. So we're going to see that in a minute. Here's an important example. In this example, several ideas are going to come up. So we're going to kind of be patient after a couple examples, see everything that's going on. There's kind of a lot of concepts going on here. But here I have some data points. The data points are in black. I have 5 data points. And I have a line that kind of is a pretty good line that passes through them. I don't know if this is the best line. Actually, we're going to talk about what best means. But it's a pretty good line. And the equation for the line is given down here, right here. So remember, the little hat on y means that this is a prediction. That's the job of our equation. Based on the data, make predictions. If you give me an x value, my equation predicts what the y value would be. So this particular equation says y hat equals 0.8x plus 2. Okay, here we go. So what we're going to do is find the difference between the actual y value of the data point and the y value on the line. So for this first point, when x equals 2, the actual y value is 3. That's the value of the data. When x is 2, the data point is at 3. Now, if I plug 2 into the equation, I get 3.6. Where did that come from? Well, I did 0.8 times 2, because that's what x is, plus 2. When I do 0.8 times 2 plus 2, I get 3.6. So my estimate is too big. My estimate is greater than the actual value. All right, so to calculate what's called the residual is that vertical distance. We do the actual minus predicted. So this is an important formula, so I'm going to write it up here. Residual equals actual minus predicted. Okay, the actual y value minus the predicted y value. 3 minus 3.6 is negative 0.6. Okay, now I put the ones that turn out negative in red. If the data value is below the graph, the actual value is less than the line, then residuals will be negative. If the data value is above the line, the actual y value minus the predicted y value will be positive. So the negative residuals I drew in red, the positive ones I drew in blue. Okay, so now let's do data point 3. The actual y value is 6 from the data, but when I put it into the equation, I get 4.4. That's because 0.8 times 3 plus 2 is 4.4. That's where that came from. I just put it into the equation for y hat. If I subtract, I get the error. And as predicted, it's positive because the actual value was bigger than the predicted value. The data value was above the line. Okay, so these residuals, remember, are the vertical distances. They're negative if the data point's below, positive if the data point's above. All right, let's put in 5. When we put in 5 into our equation, we get 6 for the y value. 5 minus 6 is -1. That's the error. So this one, the error was -1. When we put in 7, we see that the error is going to be negative, and it's going to be less than, in size, it's going to be in between 0 and -1. So when we put in 7, we get 7.6. And 7 minus 7.6 is -0.6. And finally, when we put in 8, the last data value, we get 8.4 for our predicted value. And 9 minus 8.4 is 0.6. Now, if we add up the residuals, there's a problem. They kind of cancel each other out because we have some positive ones and negative ones. We want all the errors to count. Okay, so kind of like we did in standard deviation, we square them. So this is where the least squares comes in. So we square the residuals and we get 0.36 and we get 2.56 when we square this one. -1 squared is 1. -0.6 squared is 0.36. 0.6 squared is 0.36 also. And when we add them up, we get 4.64. All right, that's what's called the total squared error. I'm going to call it TSE. That's how we evaluate how good a line is. It's the squares of the residuals. So you find each residual, square it, and add those up. That's a measure of how good the line is. Okay. All right. In my next graph, I'm going to complete 2 tables, and we'll try to plow through this so it doesn't take too long. But I have the same data set in both graphs. We have 4 data points. The first graph has an okay line. It looks pretty good. Comes pretty close to the points. And it is y hat equals -0.5x plus 6. The second line here is not very different. The y-intercept is a little bit bigger, and actually the line has a more negative slope. This line is actually what my calculator calculates to be the very best line. So it's a little bit better than the first one, and we're going to see that its total squared error should be less. All right, so we're going to get in the habit of calculating this table. This table, we're going to find the predicted values, the residuals, and square them and find the total squared error. All right, here we go. So I'm going to kind of go through this quickly. When we put in 1 into the equation, the actual value is 6, predicted value is 5.5. If we subtract them, we get 0.5. Okay, when we put in 2, the actual value is 5, and the residual is -1, because 4 minus 5 is -1. When we put in x equals 4 into the equation, we get we get 4. Yeah, I can see that from the graph. 4, go up to the line, it's 4. 5 minus 4 is 1. And then when I put in 5, I get 3.5. 2 minus 3.5 is -1.5. Square them. So it makes them all positive. 0.25, 1, 1, and 2.25. And when I add them up, total squared error for this line is 4.5. Now, depends on how much data is. The total squared error is relative in the sense that it might be big. The question is it the best it can be? So the size of the total squared error really isn't that important right now. It's just, are we getting the best we can get with the line? All right, this dude should be a little bit better. It's a little bit more complicated equation, so I'm going to have some more decimals. But I'm going to do the same thing. When I put 1 into the equation, I get 5.65. When I put 2 into the equation, I get 4.95. When I put 3 into the equation, or 4 into the equation, I get 3.55. And when I put 5 into the equation, I get 7.85. So all of these came from the equation. Now, I just subtract to find the residuals, and I get 0.35, negative 0.95, 1.45, and I get negative 0.85. Wow, I actually get something a lot bigger than that. 7.85, 2, I get negative 5.85. Okay, so when we add them up and square it, oh, I'm sorry, that's because this should be 2.85. I can't even read my own writing. And negative 0.85. So cross that out, negative 0.85. That's better. So when I square them and add them up, I get 0.1225. A lot of crazy decimals. 0.9025 and 2.10 with a little bit of rounding, and 0.72 with a little bit of rounding. The bottom line is when I use my calculator to do this, I get 3.85 for the total squared error. So if we had to judge which line is better, I certainly like the first one because not as many decimals, but the second line does a better job of reducing the total squared error. All right, I want to look at a couple of visualizations and we'll be done here. Here's a kind of a cool way to picture this. And this is kind of a very famous diagram. We have squares drawn. What are these squares? Well, the red line, that is our line, hopefully a good fit to the data. This one may not be the best one, but that's a line we're fitting to the data. The little blue points are the data. Now, here's how they made the squares. They drew in the residual, like here. That's the residual. That's the error. And since we find all the residuals and square them, that's what they did visually. The area of the square right here and that one, that's the squares of the errors. So if we add those blue squares, we get the total squared error. The total squared error is the sum of the areas. Okay, so this is a visual way to tell how good our line is doing. The line that makes these blue areas as small as possible is the line of best fit. Okay, so that's what we're computing in the table. All right, so I got a little site here. What this program allows me to do is if I can change the line. So I can move the line around to try to make these as small as possible. So if you look way down here, this line is horrible. It misses almost all the data. It has one data point below it and the rest above it. You can see that the errors are huge. And the area of the squares, it tells me, is 1,235 right there. And if I go up here, same thing, it's kind of bad. I can move this other point around too. In fact, if I go the wrong direction, the association was positive, but if I use a line with negative slope, we see the error is huge. Okay, so the goal is to kind of try to find a line where the total squared error is as small as possible. And this is kind of a better way of seeing it. In the table, which is useful for actually computing it, kind of hard to see what's going on. But that's what we're computing in the table, the area of these squares, and we're adding them up. So this is not too bad. I got the squared error down to 424.6, but I'm going to see what the best is. Ooh, hey, I wasn't bad. If you click this little thing that says least squares line, it puts in the very best line, and that makes the area of the squares as small as possible. And right here where my cursor is, you see that the best we can do is 422.35. Like I said, our goal is to make them as small as possible. All right, and this is the line that does it. Okay, so we'll be practicing this in class. For your journal assignment today, I want you to try computing one of these tables yourself. So we're going to compute the total squared error for this line. We have 4 data points, and we have this nice blue line that kind of passes through them. And the equation for the line is down here. So you're going to use this to find the predicted values. You square it. So complete the table, add them up, find the total squared error.